welcome back. So today, so I'm going to talk about the four topics: the Schrödinger equation, then tunneling effect, quantum state of the atom, and laser. Most of the time, I would say most of the time for the Schrödinger equation and the quantum state of the atom. Okay, so what is the main goal of the Schrödinger equation? So basically, so far we learned that the particle with a small mass and high speed can have the wave behavior. Especially the one of important particle with such behavior is electron. So the main goal of the Schrödinger equation is to explain, to model the behavior of the electron around the atoms. So once you understand the behavior of the atom, the electron, then you can understand the behavior of the atom, and also you can understand the bonding between atoms, and even bigger, scale. Oh, sorry, I just noticed that I'm muted. Okay, then let me start it again. So today I'm going to cover the four topics: the Schrödinger equation, tunneling effect, quantum state of an atom, and laser. And I will spend the most of the time for Schrödinger equation and quantum state of an atom today. Okay, so let's start from the Schrödinger equations. So what is the main goal of the Schrödinger equation? So it is to explain or model the behavior of the electron around the atoms. So to explain that behavior and develop the model, so Schrödinger defined these equations, and then we started applying this equation to the one-dimensional the barriers for easier understanding. So at first we learned that this electron has a behavior of the wave by the de Broglie's the wave and particle duality. So we can define the wave function of the electron right here as a function of the space and the time. And since it is wave, it has a sinusoidal function, as you can see here. Okay, then you can define, so we can have this one-dimensional time-independent Schrödinger equation, as you can see here. So even when I look this Schrödinger equation at first time when I was young, like you, I was so scared. So all the signs look so complicated. But notice that there are three simple terms, three simple components. Then can you tell me what they are? Please answer this question. Which of the following is not the component of the Schrödinger equations? Alright, very good. Thank you for your response. Yes, so the answer is nuclear energy in here. So this Schrödinger equation consists of the three components: the kinetic energy of the electron, the wave, the kinetic energy of the wave of the electron, and potential energy of the wave, and total energy, as you can see here. So this total energy is the sum of the kinetic energy and the potential energy of this wave in the system. Alright, since it is the one-dimensional time-independent Schrödinger equation, that means it is most simple form of the Schrödinger equation. So as you can see here, so we remove the time variable, and so we only have the x variable for the space because it is one-dimensional equation. And then so we set the boundary conditions for one-dimensional at the boundary at x equals x0, or sometimes you can set x equals 0 depending on where the boundary is located. For example, right here. So let's say we have a potential barrier, the potential step function right here, and the height of the potential is u0, and in this region, the potential energy is 0. Then we have the boundary interface at x equals 0 right here. Then we can have certain wave function. This is the function of x because it is the time independent. Okay, then what boundary condition can we use? Number one, we can use the continuity. We need to consider two continuity. The one is continuity of the wave function. So as you can see here, this line at this boundary is continuous. Since it is continuous, this wave function at x equals x0 minus, or in this case, we can say this x is 0 minus equals to x equals 0 plus. So we need to consider this continuity of the wave function itself. And next, you need to consider the continuity of the first derivative of the wave function right here. So from this continuity, you can have the two equations using for these Schrödinger equations. And another, the boundary condition is always the total probability is 1. So how do you calculate the probability? So this is the square of the wave function, and you have an integral from negative infinity to the infinity. Right? Then this equation should be 1. Then from here, then you can have another equation. So yes, in the one-dimensional problem, when you have this barrier, you can use these three boundary conditions. Okay, so in one-dimensional box right here, assuming we have the wave of the electron, then we can have a various mode of the standing wave, as you can see here. So this is the first mode, second, and third mode. Then the square of the wave function, which is the probability density, its shape is right here. This is the first mode, second, and third. So at the boundary, its probability has to be 0, and also the wave function has to be 0. So considering this boundary condition, this one-dimensional time-independent Schrödinger equation can be simplified as you can see here. So another condition is when the electron moves in the free space without any constraint, then the potential energy 0, which is U is equals 0. So this term is disappeared, then you can have this simple equation. I know it's not still simple, but better than this. Okay, and in this equation, you can apply these boundary conditions. The wave function at 0 and L is 0, and the square of the wave function is 0 at x equals 0 and x equals L. So once you apply this boundary condition, eventually you can define the energy, the total energy E from this equation as a function of the width of these barriers and the principal quantum number n. So this energy is proportional to the square of the principal quantum number n. They are integer, as you know. So depending on the n value, this is n, is increasing from 1 to 4, then we have this discrete energy level of the electron in this one-dimensional box. Okay, then let's try several example questions about the Schrödinger equation in one-dimensional box. So this is the previous past year exam question. A collection of electrons are trapped by one-dimensional quantum box of length 1.5 a within the region x from 0 to 1.5 a. Question A. Show that the wave function equals root 4 over 3a sine knx is a solution of the Schrödinger equation for u equals 0 in the box and express kn in terms of a. So this kn is wave number, then we want to express this wave number as in terms of a right here. Okay, then second question. Write a wavelength lambda 0 illuminates electrons at the ground state of the quantum box, resulting in the transition of the electrons to an excited state. Okay, as you can see here, so ground state means this electron in this one-dimensional quantum box has a first mode of the standing wave, as you can see here. But if you shine the light, that means you provide photon energy to this electron, then it can excite it to the certain energy level. So it can have a second mode, third mode, or fourth mode of the wave, depending on the added photon energy. Okay, so in this question, we added illuminate the light of the wavelength lambda 0. That means we added photon energy to the electron at the ground state. Then it is excited to the certain excited state. Given that the wave function of the electrons at the excited state is right here, find the wavelength lambda 0 as a function of a. Okay, so we have two questions. So, okay, let's solve the first question. In here, we need to use the Schrödinger equation for one-dimensional box. So, Schrödinger equation has three components. First one is kinetic energy. Second, potential energy. Third, total energy of the system. But in here, potential energy is 0. So in the Schrödinger equation, we only have two terms for the kinetic energy and total energy terms. Okay, having this, then to show that the wave function has this form, we just apply this wave function to this simplified Schrödinger equation. Then if this equation is valid, then we can show that the wave function can have this form. And also, in the meantime, we can define the wave number Kn in terms of A from this equation. Okay, then let's try. So as you can see here, in this Schrödinger equation, we have the wave function right here, and we have a second derivatives of the wave function. So at first, we want to define the second derivatives of the wave function using this given equation. Okay, so this is the wave function. Same with this. Then once you do the differentiation of this, then you have minus kn root 4/3a cosine knx by the differentiation of the sine function. Then let's do the differentiation one more time. So the second derivatives of the wave function is negative kn square root 4/3a, so we keep this constant, and the cosine knx becomes sine knx. So we define the second derivatives of the wave function right here. Okay, then let's apply this term to here in the Schrödinger equation, and this wave function will be applied to this side, the right hand side of the equation. Okay, so this the left hand side is, so we cancel these negative signs, so we have h bar square kn square divided by 2m times this constant times sine knx. Okay, the right hand side, E, the energy, times this wave function, the constant times sine knx. So now this constant inside of the root is cancelled out. Sine function is cancelled out as well. So eventually you can define the energy E equals h bar square kn2 square over 2m. So yes, this wave function is valid solution of the Schrödinger equation when this constant h bar square kn square over 2m equals to the total energy E. Okay, and then let's move on. Let's move on to question B. Light of the wavelength lambda 0 illuminates electrons at the ground state of the quantum box, resulting in the transition of the electron to an excited state. Given that the wave function of the electrons at the excited state is here, find the wavelength lambda 0 as a function of A. Okay, so we can use the energy, the quantized energy of the quantum box right here. So we already defined this. The total energy is h bar square kn square over 2m. Then this is h square n square over 8ml square. So this is the energy level of the electron in the one-dimensional quantum box. We already have this equation. Then, what is L? L is 1.5 A right here. So, if you from this equation, you can simplify this h bar square kn square from this. Actually, this right. These mass terms are cancelled out, and this 2 is the 8 is divided by 2. So the h bar square kn square equals h square n square, the numerator over 9a squared. So this 9 is 4 times 1.5 squared. So from here, you can define Kn. Kn is NH over 3A H bar. So H over H bar is 2 pi. So Kn is 2n pi over 3A. So we express Kn in terms of A. Okay, then let's define define the wavelength lambda 0. Okay, the excited electron has a form of this wave function, and the original form of wave function is right here, the root 4 over 3a times sine knx. Then now, once it is excited, we have this equation, root 4 3a sine 8 pi over 3a, right here, 8 pi over 3a. Then, what is Kn? We already defined Kn here. So Kn is 2n pi over 3a. So, from this equation, the constant outside of sine is same. So that means this 2n pi over 3a has to be equals to 8 pi over 3a. So from this equation, you can find the principal quantum number n, which is 4. Okay, now we found n value, n equals 4. So by the photon energy of the wavelength lambda 0, the electron is excited from ground state, n equals 1 to n equals 4. Okay, then delta E, the change of the energy, equals to the photon energy, E photon. And how do you define the photon energy? Remember this equation, photon energy is hc, the Planck constant, times speed of the light, divided by wavelength, lambda 0. And it is E4, the energy level when n equals 4, minus energy level at the ground state, E1. Then, how do you define the energy? Energy equation is here. So E is h square n square over 8mL square. So this delta E is h square over 8m 1.58 square, L is 1.58, times 4 square, n is 4, minus 1 square, so which is 15. So it is 15 h square over 18 ma square. Again, it is 5 over 6. Okay, then let's use this term, the photon energy, and this. So h is cancelled out, and you can define the lambda. Lambda equals 6 mca square over 5h. So yes, the wavelength is the function of A. So this is the answer of the question. Okay, any question for this? So if you have questions, just feel free to type the text or unmute your mic. Okay, then let's move on. Next question. An electron is trapped at the ground level of an infinity deep quantum well with a width of 0.2 nanometer. Number 1, determine the ground level energy when n equals 1. Number 2, after the electron observes a photon, it is excited up to the second excited level, which is n equals 3. Determine the wavelength of the photon. Okay, at first let's define the ground level energy. So you can use this equation. The energy of the electron at this one-dimensional quantum box is h squared n squared over 8ml squared. Then this is the Planck constant, and this is the effective mass of electron, m. And what is L? L is 0.2 nanometer. So it is 1.5. Of course, now n equals 1. So it is 1.5 10 to the negative 18 joule, which is 9.3 electron volt. Okay, then now the electron is excited from ground level to n equals 3 by the photon energy absorption. Then delta E is photon energy, which is hc over lambda 0. Then it is the difference of the energy level for n equals 1 and n equals 3. So E3 minus E1. So these energy terms has the same constant, h squared over 8ml squared. Then it is multiplied by 3 squared minus 1 squared. So this is 8, and 8s are cancelled out. So this photon energy is h squared over ml squared. Then let's define lambda 0. Lambda 0 is hc. So this term goes to here, then you can move this term to here. Of course, you need to invert it. So lambda 0 equals hc ml squared over h squared. So you have cm l squared over h, the Planck constant. So c is the speed of the light, m is the effective mass of electron, and l is 0.2 nanometer. H is Planck constant. So it is 16.5 nanometer. So this is the answer of the second question right here. Okay, so the concept of the Schrödinger equation might be difficult because it is totally far from our real life. So it might be hard to accept it, but as long as you understand the Schrödinger equation consists of the 3 terms of the kinetic energy, potential energy, and total energy. Then if you use the boundary conditions, the continuity and the total probability is 1, then you can easily approach the questions. Okay, then I want to spend one slide for the tunneling effect because I want to spend more time for the quantum status of the electron in the atoms. Okay, so let's say we have a traveling particle and we have a certain barrier, the potential barrier. Then in the classic physics, if the kinetic energy of this particle is less than this barrier, then it cannot penetrate at all. And once this kinetic energy of the particle is larger than this potential, all of the particle can penetrate. this barrier. But in the quantum physics, since it has a wave behavior, it can penetrate, some portion of the energy can penetrate through this potential barrier, although its energy level is less than this height of the potential barrier. So, considering this wave equation and the boundary conditions at this barrier, you can define the transmittance ratio P as a function of the width of the barrier and energy difference. U is the potential of the barrier and E is the total energy of the system. Then you can define this transmittance, and if the electron is not transmitted, then the remaining one is reflected. So you can easily define the reflectance rate R equals 1 minus T. So remaining one is reflected. Okay, then let's move on to the next topic, the quantum state of an atom. So again, we want to understand the electron behavior around the atom, because once we have the solid understanding of it, we can explain the bonding between the atoms, and also we can moving to the bigger scale, like crystalline structure of material, and in the end we can understand or predict the material properties considering this electron behavior of the atoms for each element. So we are trying to develop the mathematical model to explain that. Then one of the most recent and well-matched mathematical model is Schrödinger equation. Okay, so this topic is for the quantum state of an atom. So there are the 4 kinds of the quantum numbers to state the quantum state of the electron of the atoms, and depending on what quantum number the electron has, it can have the different various shape of the orbitals. So basically you can understand the orbital is the cloud of the electrons. And this one, okay, I'll explain this orbital in the next slide. Then, okay, so in here we have actually in this table we only have 3 kinds of quantum numbers: the principal quantum number, orbital quantum number, and orbital magnetic quantum number. And the last one is the magnetic spin quantum number. So basically you can understand these numbers as an address of an electron. For example, so let's say we have the carbon. Then what is the atomic number of carbon? Carbon is 6. That means in the neutral state, carbon has 6 electrons. Then we want to define the status of the 6 electrons one by one. So then we gave the address of the electron one by one. So okay, so when you use the address, for example, you are sending some package to your friend. Okay, then at first you need to define which country you want to send this package. And after that, so the country is the biggest category. And after that, you define the state. Is the second hierarchy, right? And after that, you define the city. Then you may define the street number and the actual address in the end. So you are narrowing down the category, so to define the specific address of the place. It is same we have the four category of the address of the electron. The biggest one is, the largest one is principal quantum number. Basically, it defines the number of shells of the electron cloud. Then second one is orbital quantum number. So each shell of the electron cloud has their own specific shape. So this orbital quantum number defines the shape of the electron clouds. The next one is magnetic quantum number. It defines the direction of it. The coordinate of the electron clouds. Then last, the spin quantum number defines spin up, the direction of the spin of the electron, spin up, spin down, right? Okay, then what is the origin of this quantum number? Actually, yes, four quantum numbers. Then these Schrödinger equations defines these three quantum numbers: principal quantum number, orbital quantum number, and magnetic orbital quantum number. Don't be scared. I'm not going to ask you to derive these equations. So let's just take a look where these three quantum numbers are coming from. So in the previous topic, you learned about the one-dimensional time-independent Schrödinger equations. So we had three terms: kinetic energy, potential energy, total energy. Since it is time-independent, we don't have a time variable, and it is one-dimensional problem, so we only have x variable for the space. But let's think about, for example, hydrogen atoms. So electrons are existing in three-dimensional space. So to understand, to define the equation for the electron in the hydrogen atom, we need to use three-dimensional time-independent Schrödinger equations. Okay, difference is dimension, 1D, 3D. Then, hydrogen. So we can assume that hydrogen has the axisymmetric system. So we can use the spherical coordination. So instead of using only x right here, this wave function has three variables for three-dimensional coordination: r, theta, phi. These variables are for the spherical coordination. So wave functions has three variables. Then instead of the second derivatives, we have second del, the gradient, right here. And then another condition is, now the electron is bounded by the proton of the hydrogen atom. So it has a certain potential energy. So the potential energy is defined by Coulombic force between electron and proton. So the potential energy has a form of the potential energy for the Coulombic force. Then this term is applied to here, the U terms. And then eventually you can define the energy, total energy of the electron as a function of the principal quantum number n. So actually when we derive the equation of the total energy of the electron, yes, it is very well matched with Bohr's model. So I hope you remember we already defined this energy of the electron, energy level of the electron, using the Bohr's model. Okay, then Schrödinger equation also can define this equation. Same with Bohr's model. Then, actually the limitation of the Bohr's model is it is working well with hydrogen atom because it only had one electron. But it didn't work for the more complicated system, larger atoms like a carbon, gold, something like that. But these Schrödinger equations can explain not only the hydrogen model, it could explain more complicated atoms with multiple electrons. Then, okay, in here we could define the energy level of the electron for hydrogen right here. And also from this equation, the Schrödinger defined the wave function as a function of the three coordinate r, pi, b, r, theta, b right here. Then then this equation has three terms, and then eventually you can define the solution. It's very complicated, so don't try to understand. So this is the wave function solution for the hydrogen. So this is the function of r, theta, b. Then you can notice that there are three integers. N is here, L is here, and M is here. I'm not going to explain how we have these integers in this solution. Then, okay, anyway, Schrödinger was a very clever person. Then he got the solution right here. Then we have these three kind of integers. They are three quantum numbers. N is principal quantum number, L is orbital quantum number, M is orbital magnetic quantum numbers. Okay, then we already learned that the probability of the existence of electron is defined by the square of the absolute value of the wave function. So, if you apply this solution to this probability, and also if you visualize this probability as a function of space in this spherical coordinate, you can visualize the shape of the electron cloud shell for these three quantum numbers. Okay, so I quickly move on this part. So n is the principal quantum number, 1, 2, 3, 4. So it has integer. So it defines the shell of the electron clouds. And for the hydrogen model, yes, we can define energy level for this principal quantum number. Orbital quantum number is, its range is determined by n. So it is from 0 to n minus 1. So if n is 1, we only have 0 value of the L. If n is 4, then L can be from 0 to 3. Then it defines the shape of the orbital, SPDF. So you use these spectroscopic notations when you write the electron configurations. Okay, so orbital magnetic quantum numbers has a range of from negative L to L. So if L is 2, ML is varied from negative 2 to 2. So 5 choices. And the last one is spin magnetic quantum number. So it is not defined in the Schrödinger equations, but for every 3 quantum state, so you can have 2 possibilities. The one is spin up, the other one is spin down. Okay, then coming back to the orbitals. So this is the probability, the square of the absolute value of the wave function. Then if you draw this function in this three-dimensional space, you can define the shape of the orbitals, as you can see here. So how do we define this? We draw the contour of the 90% of the probability of the electron existence in these equations. So in one dimensional, this probability has certain curve like this with a certain distribution. Then we cut at the 90%. So for example, this shell looks like a sphere, but it is actually shell with a contour of the 90% of the probability. So when you have a different three quantum numbers, n, l, m, then you can actually have a different shape. So especially the overall shape of the orbital, the electron cloud, is determined by this orbital quantum number L. So when L is 0, it has a spherical shell, and when L is 1, it has a dumbbell shape. So it is varied. Then this M, magnetic quantum number, determines the coordination of the orbitals. Okay, so this video may show you how the electron clouds are formed depending on the quantum numbers. So at first we have hydrogen. Hydrogen has one electron, so it has a s orbital. Helium add one more electron in the same orbital because it has a spin up and spin down. Then S2, 2p, so it has a dumbbell shape. And we have another shell of the sphere for n equals 3. And we add the p orbitals, dumbbell shape, for 3 directions. Then, yes, we keep adding the cloud of the electrons. So this is how the electrons are existing along the nucleus of the atoms depending on the quantum numbers, the 4 addresses. Okay, next. And this is how to write the address. So expressing the orbital occupancy. So at first you can use the orbital box diagram. For example, for lithium, you can have the boxes for 1s, 2s, and 2p. And each box can contain 2 electrons, spin up, spin down, as you can see here. So s orbital can have 2 electrons, and p orbital has 3 boxes. And each box can have 2 electrons. So you can express the quantum number, 4 quantum numbers using this orbital box diagram. So this box diagram can express the 4 quantum numbers, but it's too complicated. So most time we prefer to use this electronic configuration. It is more simple, but it doesn't express the magnetic quantum number and the spin quantum number. It only expresses the principal quantum number n and L using the spectroscopic notations SPDF. So, for example, this is the example of the nitrogen, I guess, number 7. So it is 1s2. At first, 2 electrons occupies the first s orbital, and we move on to the second shell. The 2s2 and the remaining electron is 3. So the 3 electrons occupying p orbitals right here. So these black numbers represent the number of electrons in each orbitals, and this alphabet represents the spectroscopic, the shape of the orbital. The red numbers are principal quantum numbers. Okay, then let's try a couple of example questions. For a spherically symmetric state of the hydrogen atom, the Schrödinger equation in spherical coordinate is here. Show that the 1s wave function for an electron in hydrogen is right here. So this is a wave function when n equals 1. Satisfies the Schrödinger equation. B. What is the energy of the atom for this state? Okay, like the previous question, if you want to show that this one is the wave function of this equation, we just apply this to this equation and show that it is valid. Okay, to apply this equation to the Schrödinger equation, we need to find the derivatives of this wave function and also the second derivatives. Okay, then let's see the first derivatives. So we keep this constant 1 over root pi a cube and d over dl exponential negative r over a0. Then okay, it is a differentiation of the exponential function. So we have minus 1 over root pi a cube times 1 over a0 from here, and we have the same function e exponential minus r over a0. Okay, then you can notice that we still have the wave function. So this constant and exponential term. So the derivatives of the wave function is minus wave function over a0. Then let's do the second derivatives. Second derivatives is d over dl, d wave function over dr. And what is the derivatives of the wave function? Right here. So it is d over dr times minus wave function over a0. So it is again, you can take out this constant minus 1 over a0 and derivatives of the wave function. So it is wave function over a square. So now you can apply the second derivatives and wave function to this given equation, the Schrödinger equation. Okay, at first we have a second derivatives. This term is here, the wave function over a square, and we apply the derivatives this term. So second term is minus 2 over r wave function over a0. Then we keep the other terms, and then you can notice that these wave functions are cancelled out. These wave functions are cancelled out, and you can define this h bar square equals to mk e square a0, when a0 is Bohr's radius for the hydrogen atoms. So you can apply this term to here, h bar square. Then, okay, so once it is applied to here, the mass term is cancelled out. So we have minus k e square a0 from here, divided by 2, and since the wave functions are cancelled out, we have 1 over a square minus 2a0r minus ke square over r equals e. Okay, then let's take a look. This constant and this second term. So a0 is cancelled out, 2 is cancelled out, so we have ke square over r for this. And for the first term, we have minus ke square over 2a. Then now you can find that these two terms are cancelled out because they are same. This one and this one are cancelled out. So the energy is minus ke square over 2a0. So this is the ground state of energy of the hydrogen. So we can say the Schrödinger equation is satisfied, then this wave function is valid for first 1s wave function. Okay, the next question is what is energy of the atom for this state? Yes, we already calculated the energy right here. Okay, then let's move on to the next question. List down all quantum states for the principal quantum number n equals 3 and hence determine the maximum number of electrons for n equals 3. By constructing the quantum state of the various n, verify that the maximum number of electrons for in the principal quantum number n in 2n squared. So I hope that this question helped you being familiarized of the writing the quantum numbers. Okay, so we have the 4 quantum numbers: principal, orbital, magnetic, and spin quantum numbers. So when n equals 1, the electron is sitting at the K shell, the first shell, the closest to the nucleus. When n is 1, we can have only 0 for L, which is s orbital. M is 0, then now you can consider spin up, spin down. So the quantum state is 1, 0, 0, 1 over 2. 1, 0, 0, minus 1 over 2. The notation is 1s, then you can have 2 states and 2 electrons. Okay, then let's move on to the next shell. The notation is large L, the second shell. N is 2, then now we can have 2 L values, 0, 1. This is for s orbital, the spherical shape, and p is for dumbbell shape. In the dumbbell shape, we have 3 magnetic quantum number, negative 1, 0, 1. And each magnetic quantum number, we have 2 electrons, spin up, spin down. So we have a 2s, 2p. And next one, n equals 3. So the notation of the shell is m, the third shell. So we have 3 kind of orbital quantum number, 0, 1, 2. So the notation, spectroscopic notation is SPD. We have s orbital, p orbital and d orbital. For d orbital, we have 5 magnetic quantum numbers from -2 to 2. Then we have spin up, spin down, 2 electrons. Okay, then let's count the number of electrons right here. When n equals 1, we have 2 electrons. When n equals 2, we have 8 electrons. When n equals 3, we have 18 electrons. So you can say the number of electron is the function of n, which is 2 times n squared. So if n is 1, it is 2. When n is 2, it is 8. When n is 3, it is 18. So we can also have the mathematical derivation right here. So this is the number of electron for n. N is in here I is varied from 1 to n. Alright, then the inside of this parenthesis is number of the magnetic quantum number. So when you have an n value, what is the number of the L, the orbital quantum number? It is from 0 to n minus 1. Then m, the magnetic quantum number, has a range of the negative L to L. Right? So the number of these numbers is 2i minus 1 plus 1. This is for 0. Okay, then now we need to consider spin up, spin down. So we multiply 2 right here. Okay, then next is the matter of the mathematics. So we have a 2 here outside of sigma, and the n is varied from 1. So L value is varied from 1 to n. So it is 2i minus 1.
You are muted, bro.
Okay, thank you. So was I muted for a long time?
Like for a few seconds.
Oh, okay, I got it. Thanks. Okay, then from this equation, so this 2 is for spin up, spin down. So we multiply by 2. Then this one goes to here outside of the sigma. And we have inside this parenthesis, we have 2i minus 1. Then we have 2 times, for this 2i, we have 2 n times n plus 1 divided by 2. For this negative 1, we have negative 1 right here. So eventually, we have 2n squared. Alright, so I hope that you are familiarized for of this, the writing, defining the quantum state of the electrons. Okay, then let's move on. The last topic, the laser and laser light. So in the laser, we need to consider the 3 specific phenomena. The first one is stimulated absorption. We already learned about this stimulated absorption a lot. So we have these 2 energy level, and the electrons are sitting in the ground state, E equals 1. Then once you shine the light, this electron absorbs photon energy. Then this electron is excited to the next energy level. So this is the stimulated absorption. So the photon energy stimulate electron, then it is jumped to the next energy level by absorbing the energy. Next, spontaneous emission. So once the electron is excited and relaxed to the ground state or lower energy level, it releases energy as a form of photon. So once electron is relaxed to the ground state or lower energy level, it emits photon. So it is spontaneous emission. Okay, then in laser we use the stimulated emission. And what is stimulated emission? So in here, we already have excited electron at the higher energy level by providing certain energy. Then we shine the photon energy. Then this photon, actually this electron doesn't absorb this photon energy, but this photon energy provides certain disturbance to this electron. And then this electron, by that disturbance, this electron has the relaxation of the energy. Then eventually it emits photons. So once you apply one photon here, eventually you have two photons in the result by this stimulated emission. So this is the main principle of the laser right here. Okay, then what is the input source of the stimulating electron to the upper energy level? So in this laser, we apply the electricity or other types of the energy. Then the electron is excited to the higher energy level. Then once the one electron is relaxed, it emits photon. Then that photon stimulates the other electrons. Then, so we keep increasing the number of photons between these two mirrors. So when you have these two mirrors, the mirror 1 should have a higher reflectance than the mirror 2. Then eventually this photon energy bounce back and forth and keep causing the stimulated emission. And then since this mirror has a lower reflectance, the laser light is emitted from this mirror. Okay, this is how we have the laser by this stimulated emission. Alright, so this is all for today. Almost time's up. So I hope you enjoyed this summary lecture. And next week, I'm going to cover the previous exam in the last semester. So this is very fresh exam questions. So it must be very helpful for your preparation of the final exam. Okay, so I hope you join this class again. Right, and also I'm uploading my recorded video in the NTU Learn website. So yes, please feel free to watch it again. Alright, this is all for today. Thank you so much for your participation. Hope to see you next week again. Bye.